Yes, welcome you all for my continuation on the lecture on undamped free vibrations, undamped free vibrations of single degree of freedom systems. This is what I told you, the title of the topic. So in my last lecture I have explained the meaning of each word and what is it combined also, and how the system looks like. The system is going to be a spring mass system, and what we are going to understand, we are going to understand or determine what is called as the natural frequency of the system. And I also explain you why we find out the natural frequency of the system. So mainly, again to repeat it, to avoid what is called as resonance. We want to avoid resonance. For that purpose, I need to know what is the natural frequency of the system. Okay, how to do it, how to find it out. So we go through the various methods. I listed 4 methods in the last class itself. One is called as Newton's second law, use of Newton's second law, use of D'Alembert's principle, and by energy method and by radix method. These are 4 different methods which we can employ and get what is called as the natural frequency of the system. The first method, so probably I shall discuss the first method, Newton's second law. Law of motion, of course. Newton's second law of motion. Okay, probably you may wonder, or you may, we have studied this sometime in your 5th standard, 6th standard. When I studied, I think I studied it during my 8th standard or so. Probably now in the present syllabus, probably it is introduced much earlier. Newton's laws of motion, there are 3 laws: Newton's first law, Newton's second law, Newton's third law, all that. Okay, again that we are not going to study in detail about Newton's second law. I quickly revise it and we shall go and apply it. Apply Newton's second law for our systems, and then how we can write down what is called as the equation of motion, or what is called as, or how to find out the natural frequency of the system. Straight away we shall go to that. What is Newton's second law? So Newton's first law of motion defines force. What is meant by force? That is stated by Newton's first law. And Newton's second law says how to measure force, how to quantify force. So force is equal to ma. So F is equal to m into a. Okay, F is equal to m into a. This is Newton's second law. So the force what you apply on the body will make the body of mass m to have motion whose acceleration is a. That is the meaning. Okay, if you have a body and apply some force on it, and the mass of this body is m, then this body will start moving in this direction, in the direction of the force with an acceleration a. Okay, so now how do I write it? The same thing. I shall have this. Okay, mass multiplied by acceleration is equal to the force. The net force, what is this? The resultant. Sometimes you may not have only one force, you may have a number of forces. Okay, the left hand side is net force or net or resultant force. Resultant force or sum of all forces. Sum means the vector sum. Sum of all forces in the direction of acceleration. In the direction of acceleration. This is very important, and I keep on repeating it. What is the left hand side? The sum of all the forces in the direction of acceleration. Is equal to all this is what? This is equal to mass multiplied by the acceleration of the body. Okay, so how does it look like? Suppose I have a body of mass m, and say I have a number of forces, say F1, then I have say F2, and say I have F3, and say I have F4, something like this. And under the action of all this, okay, what are the different possibilities if you apply forces? It all depends upon what are the magnitudes of this. One possibility is the mass is not moving at all. Then there is no question of vibration, and hence there is no question. The body is said to be in equilibrium state. In that case, F1 plus F2 is equal to F3 plus F4, and hence there is no motion of that. But my question is, this body under the action of these forces, it is moving. It is moving, and it is not only moving, it is vibrating. It is vibrating. Okay, so now little later the vibration comes into picture. Right now, I want to apply Newton's second law, only Newton's second law. What does it say? The left hand side, the resultant force in the direction of acceleration. Okay, the mass is moving in this direction with an acceleration of say x double dot. The body is moving in this direction. Okay, so now what are the forces in the direction of acceleration? The force F1 is in the direction of acceleration. The left hand side I am writing F1. Then what about F2? F2 also is in the direction of acceleration, therefore this plus F2. Then this F3 is opposite to the direction of acceleration, therefore I shall write it as minus F3. And this also is opposite, minus F4. This is equal to, what is the mass of the body? Mass. What is the acceleration? X double dot. Okay, this is what I mean by the Newton's second law. This is what I am going to apply. Okay, what is the left hand side? Sum of all the forces in the direction of acceleration, which is equal to m into a. So whatever I have discussed so far, or if I write f equal to ma, that means I am talking about the linear motion, the motion along a straight line. Please remember, there is no guarantee that all the time you will have motion along a straight line. You may have angular motion, you may have rotation. So we have Newton's second law for rotation also. How does it look like? The expression very similar. F, as I said, F is a force which will make the body to move along a straight line. Then what is responsible for the rotation? It is moment or couple or torque. So let me say it is moment. Okay, moment. When I say moment is responsible for rotation. Okay, so whenever we say moment, we always say moment about what point, about what axis. Say m about O. What is O? O is the point of the body about which the rotation is taking place. So MO is equal to what is called as IO. I is the mass moment of inertia. So on the other day also I had mentioned, for rotation, mass is not just important. We want to know how the mass is distributed. That is nothing but the moment of inertia. This multiplied by alpha. So this is what is Newton's second law for angular motion. So what is the left hand side? Okay, sum of moments. If you don't have moment, you may have force. Then take moment due to that force about the point. Okay, sum of moments about what? About the point about which rotation is taking place. About which rotation. Point of rotation, that in short I can write it. Sum of moments about the point about which rotation is taking place. Rotation taking place. Okay, so I may have only one moment, or I may have a number of moments like that. In the previous I had shown F1, F2, F3, F4 like that. I may have a number of them. Add all that. Okay, rotation taking place, it is not just over, in the direction of angular acceleration, in the direction of alpha. That is equal to what is called as I naught into alpha. This is what we call it as Newton's second law. Okay, now let me use this and then find out what is the natural frequency of the system. Okay, before I really go to that, I go back and revise simple harmonic motion. I hope you remember. So we had an equation like this, x double dot plus omega square x equal to 0. Okay, so I may have, see later on when I apply for a system, I may have come across something like this, a into x double dot plus b into x equal to 0, something like this equation. Okay, I want to make this equation which looks very similar to this. So x double dot coefficient is 1. So here also I would like to have x double dot coefficient 1. How can I make it, achieve it? Divide throughout by a. So that means x double dot plus b by a into x equal to 0. So compare this equation and also compare this equation. Okay, so what is b by a? B by a is equal to omega square, or therefore omega is equal to square root of b by a. So this is what I am going to achieve now, or here also. Okay, so now let me come back and build a single degree freedom system. So what is called as the simplest single degree freedom system is what is called as spring mass system. Okay, the stiffness of this spring is K Newton per millimeter, meter, something like that. And what is this length? What is this length called as? This length is called as free length. Free length of the spring. The length of the spring measured along the axis. Okay, and when there is no load on the spring, that length is called as free length. Okay, so the mass of the spring is negligible. I shall note it down. Mass of spring is negligible. Okay, now what I do? I am going to attach a mass. Okay, I just wrote down this. I attach a mass. So when I attach mass, you know that mass is going to come down. Why? Because when I apply certain force m into g, the force I apply, and this spring shall undergo extension, and therefore the spring will come down and say, let me assume that this is the new position of the mass, what I attach. And this distance, okay, is equal to what I call it as static deflection of the spring delta st, and this is equal to mg divided by k. So it is as you apply the force mg here. When you apply the force mg, what happens? The spring is subjected to extension. It will undergo how much? Mg divided by k. And right now, this is what I mean by this is equilibrium position. This is equilibrium position. Okay, so if I draw the free body diagram of the mass now, this is the mass. Okay, let me show what are the forces that are acting. Please remember it is an equilibrium state. Okay, what are the forces that are acting? The weight of this is acting in the downward direction, mg. Okay, and what the spring is trying to do? Spring is trying to pull it back. In fact, it is trying to pull this mass back to its equilibrium position, and the spring is pulling it up. So spring force is always stiffness multiplied by what is the extension at that moment. So what is the stiffness? The stiffness is K. And what is the extension? What is the extension of the spring? This distance, this is the extension, that is equal to delta st. K into delta st, and therefore I can say that mg is equal to K into delta st. Please remember, this is not the Newton's second law what I have written. This is not. What I have done, I have applied equilibrium condition. This mass right now it is not moving. This mass is not moving at all, and therefore the forces that are acting on it must be balanced. Or in other words, the resultant force must be 0. That's what I have done. So mg is equal to k delta st. Now I introduce free vibrations. So how do I introduce? There are so many ways. I can take something and hit this mass and this is going to vibrate. Or I can take this mass, hold it and pull it and leave it. And this will continue to oscillate. Maybe up to here and here, like that, continuously. Okay? At some instant of time, let me assume that the mass is somewhere here. The mass has occupied this instant. This is at t equal to some time, t equal to t. Probably this is at t equal to 0. At t equal to 0, it is in equilibrium state. Then at t equal to t, it is allowed to undergo vibration. This is it. And so, with respect to the equilibrium position, okay, where is the mass? The mass is here. So, what is this distance or what is this? This is called as displacement. So, I shall assume that any displacement with respect to the equilibrium position, if it is in the downward direction, I call it as positive. With respect to this, if the mass is somewhere here upwards, then probably I call that displacement as negative displacement. In vibration, you will always have positive displacement and negative displacement. Okay? So this is what is x. And is this mass stationary now? It is not stationary, it is moving. And it is having what is called as acceleration also. Let me assume that the acceleration is also in the downward direction. Okay, the mass has undergone a displacement x, and please remember the spring also has stretched here. It is not only the mass which will go, and along with that the spring also undergoes a displacement, extension. Is it clear? So now, okay, please remember this mass now is not stationary. Remember, you cannot apply equilibrium condition. You cannot apply equilibrium condition. But anyway, for the sake of applying Newton's second law, I draw what is called as free body diagram. I would like to draw the free body diagram. Okay, so what is the mass? This is mass. Okay, so this has already undergone a displacement x. And remember, it is also moving in the downward direction with an acceleration of x double dot. It is not stationary. Here I didn't write any displacement or acceleration because it was stationary. But here it has undergone a displacement x with respect to the equilibrium position. And it is also moving downwards with an acceleration of x double dot. Okay, now let me show what are the forces that are acting on it. Do you agree that it has weight? Okay, the body has a weight and that weight is mg. That weight is mg. Okay. And any other force? Any other force? There is spring. There is spring here, and what the spring tries to do? The spring tries to bring it back to its equilibrium position. Okay. So the spring force, as I said always, stiffness multiplied by the displacement of the spring, extension of the spring. So how much is the extension of the spring? Please remember, so extension, anything with respect to this, beyond that the spring is extended, extension only. The free length, when the spring is of free length, the extension is 0. So anything more than free length or anything less than free length. If it is less than free length, the spring is compressed. If the length is more than free length, it is extension. The spring has been extended. Okay, so how much is the force? Extension. What is the extension? Extension with respect to this. So here the spring is extended delta S. And from here to here it is extended by x. What is the total extension? Delta ST plus x. So very similar to the one which I demonstrated, F1, F2, F3, F4. So here I have two forces. One is mg, which is acting in the downward direction. The other one is a force k into delta st plus x, which is acting in the upward direction. So now I apply what is called as Newton's second law. What is Newton's second law? The left hand side. What is the left hand side? Sum of all the forces in the direction of acceleration. What is the direction of acceleration? X double dot, which is in the downward direction. Okay, sum of all the forces in the direction of, in the downward direction. Okay, how many forces are there? I have two. Okay, among these two, which is the downward force? Mg is a downward force. Let me start with that. The Mg. Okay, this k into delta st plus x is in the upward direction, which is opposite to the acceleration, and therefore I have minus. So minus what? Minus k into delta st plus x. Okay, sum of the forces in the direction of the acceleration is equal to what? Mass is m, and multiplied by acceleration. The acceleration is x double dot. Okay, simplify this. This is equal to mg, fine, minus k into delta st minus k into x is equal to m into x double dot. Okay, so you know that mg is k delta st. Mg minus k delta st is what? That's what I have here. Mg minus k delta st. If you plug these two, what is this? This is 0. Mg minus k delta st is 0. 0 minus k into x is equal to m x double dot. I shall rewrite it. Okay, the same thing is mx double dot plus kx. This kx I shall send it to the other side, plus kx is equal to 0. This is what I was telling, ax double dot plus bx equal to 0. Okay, I don't want any coefficient for x double dot other than 1. So therefore I want to make this 1. So I want to write x double dot here. How can I do that? Divide through by m. Okay, mx double dot divided by m, that is nothing but x double dot, plus kx divided by m, that is nothing but k divided by m into x, and 0 is equal to 0 divided by m, that is nothing but 0. Okay, this is what we call it as, what is this? This is called as differential equation of motion. This we call it as differential equation of motion. X double dot plus k by m into x. And what is the equation? What this equation or this equation tells you? That this motion, we are writing the equation for this vibration motion now. This motion is simple harmonic. This motion. So because acceleration is directly proportional to displacement, therefore this is simple harmonic. And if it is simple harmonic, or what is omega? Omega is root of this term, that is equal to k by m. So omega, the unit of omega is so many radians per second. This is what we call it as, it is not just omega, omega of what kind of vibrations? Omega of free vibrations. Omega is what? Frequency. Frequency of free vibrations is known as natural frequency. Therefore, I shall write it as omega suffix n. Therefore, omega n is, or in other words, the natural frequency of a spring mass system is square root of k by m. Okay? So this is the natural frequency of the system, spring mass system. The same thing I can slightly modify it, or sometimes I may use it in a different form. Okay, k as it is, k divided by m as it is. Okay, I shall multiply it by g and divide it by g also. G cancels and the same thing. I have not done much. I am multiplying the numerator and the denominator by the term g. Okay, so now one more manipulation here. So I shall write it k, okay, into g as it is, divided by mg. Or this k I shall take it to the denominator. Okay, this k, I have taken it. What is this? mg by k, mg by k somewhere. mg by k, mg by k is what? Delta st. So this is also equal to g. G is nothing but the acceleration due to gravity divided by delta st. Okay? Sometimes even if you don't know k or m, then if you know how much static deflection it undergoes the moment you attach the mass, that itself shall decide what is the natural frequency of this. Okay, the natural frequency of this is also equal to g by delta st. So substituting the values of k, m, etc. delta st, using this you may have a numerical problem also, that also may be framed. I hope you have understood. Okay, so application of Newton's second law, what we do now onwards is simply, so you draw, you allow, you go through the system, identify what is static equilibrium quotient, check whether you can write down any equation based on that, applying the equilibrium condition, and then you set the system into free vibrations, then you arrest the mass at some position. So this is what I have done. The mass is actually moving. Please remember, it is not stopping. I have arrested it through my eyes and say that this is at time t. Then draw the free body diagram of that mass and show the different forces that are acting. Then apply the Newton's second law and write down the equation and simplify. You get a differential equation of motion, and that differential equation of motion is a simple harmonic motion, okay, whose solution is simple harmonic motion, and based on that simple harmonic motion write down what is the expression for the natural frequency. So this is what we are going to do. So on the same lines, now onwards what we do is we take different systems and go on applying this. This is how we are going to solve, and maybe in our next class, I think maybe 2-3 systems I can take. I don't have to explain you all this, and then probably I can get the natural frequency. Okay, so we will meet again and then continue our discussion.